Hello and welcome grade 10s to this lesson on investigating the parallelogram. We discover the properties of the parallelogram by studying and investigating triangles and their transformations. Before we join Amashni, I suggest you use your geometry theory book and revise parallel lines, alternate angles, corresponding angles, and co-interior angles, as these are important concepts in this lesson. Let's join her now.
Our learners have a few triangles and are trying to make a parallelogram. They already know that reflecting the triangle won't work. What do you think they can do to make a parallelogram? Let's see how they're getting on.
Well, for the rectangle we used rotation. Let's try that again.
Cool, check what I made, Haley. I used a scalene obtuse angle triangle and I rotate it like this.
Yeah, I made one using these triangles. What are they? Oh, scalene acute angle triangles.
Pretty cool stuff, eh?
Yeah.
The learners only had scalene triangles to work with. There are several ways to make a parallelogram from triangles, but we will stick with a rotation similar to the rotation used for a rectangle. Let's put in all the information that we know about the scalene obtuse angle triangle EFG. Now, in a scalene triangle, we know that no sides are equal to each other, so we can mark the sides with different markings. We also know that this is an obtuse angled scalene triangle, which means the angle here at G is greater than 90 degrees. We also know it's a scalene triangle, so the angles also must be marked with a different marking. We are now going to rotate triangle EFG. The fixed point will be the midpoint of side EF, which is H in this figure. To keep it fixed, you can hold it down at H. If you're using a cardboard shape, you can put a pin in it, just like our learners did. The midpoint is on the longest side. After we rotated the triangle EFG through 180 degrees, we've created a new shape. Now, I've called this new point here I. Let's mark our original triangle with all the sides and angles. Now, when we rotated the red triangle, it moved all the way around like this. This means that side EG rotated all the way around to become IF. This means that EG is equal in length to IF. Now if you look at the side GF, GF rotated all the way around here and became EI. This means that GF is equal in length to EI. Now let's look at the angles. We know that this angle here at E rotated all the way and became this angle here at F. If you look at this angle here at F, it rotated all the way and became this angle here at E. Angle G rotated all the way around and became angle I. Wow, we have made a parallelogram. Can you identify any of the properties of the parallelogram? Let's start with the lengths of the sides. We know that EG is equal in length to IF. We also know that EI is equal in length to GF. This means that in a parallelogram, the opposite sides are equal to each other. Another very interesting thing about the lines of this shape should be mentioned here. The opposite sides are parallel to each other. They certainly look parallel, but well, we're mathematicians, right? So we need to prove it. Can you see a way of proving that these sides are parallel? It will help to get some angles equal. Do you remember the alternate angles? The Z shape. So in our diagram, we can see that this angle at E is alternate to this angle at F. Now, if the alternate angles on a transversal are equal, then the two arms of the Z will be parallel. Right. If this angle is equal to this angle, then we can show that EI is parallel to GF. So let's have a look. Are these two angles equal? Let's rotate the triangle again to check. Oh yes, they are. So EI is parallel to FG, and we mark it like this. So they are parallel to each other. Now, which angles do we need to check if we want to show that EG is parallel to IF? Can you see? Now we have the Z shape. So we can see that this angle here at F is equal to this angle here at E because they have the same markings. This angle at E and this angle at F are also alternate to each other. This means that EG must be parallel to IF, and we mark this like this. Look at all the information we have in our parallelogram. Can you identify more properties of the parallelogram? I see that the opposite angles are equal to one another. Let's have a look. This angle at I is equal to this angle at G. They have the same markings. And if we look here, this angle at E has a dot plus a tick as a marking. And if we look at angle F, it also has a dot and a tick. This means that angle E and angle F are also equal. Do you see that the parallelogram also has two diagonals? EF is one and GI is the other. Do you think the diagonals are equal to each other? Well, I'm going to use a ruler to check this. Have a look. There's not a chance IG is equal in length to EF. So the diagonals are definitely not equal. What about looking at the angles at the corners of the parallelogram? Do you think the diagonals bisect these angles? That would make this angle at E equal to that angle at E. Let's use a cutout that Wesley made to check this. Again, let's move this triangle around and then compare the sizes of the angles. If we rotate the triangle, you see that this angle moved to here, this angle moved to there. Now, watch what happens. If we flip the triangle like this, we see that the angles do not fit on top of one another and are therefore not equal. And if we look on this side, we see that this angle is bigger than the one underneath. This information is enough to say that the diagonals do not bisect the angles of the parallelogram. Do you think the diagonals could bisect each other? In other words, do you think we could find out whether this line is equal to this line or this line is equal to this line? Some of you might think of congruency of triangles as a way to check. Excellent. Which triangles will need to be congruent? In other words, exactly the same shape and size. These big triangles don't tell us about these parts of the diagonals. I've made a cutout that fits the size of this triangle over here. Now I want to see if it fits this triangle here exactly. Now surely that will tell us about the parts of the diagonals that we want. I'm going to turn this triangle, I'm going to rotate this triangle like this. Do you see that this bit of the diagonal is equal to this bit and this bit is equal to this bit? Just what we wanted. So the diagonals of this parallelogram do bisect each other. Now let's take a careful look at the number of lines of symmetry that the parallelogram might have. What do you predict? So, the parallelogram has no lines of symmetry. I bet you didn't expect that. It does look symmetrical somehow, don't you think? You see, don't assume anything. Always test it carefully. Now let's look again at what was covered in this lesson. Remember, we created our parallelogram by rotating the scalene obtuse angle triangle around the midpoint H for 180 degrees. We can now say that a parallelogram is a special quadrilateral where two pairs of opposite sides are equal, two pairs of opposite sides are parallel, two pairs of opposite angles are equal, and the diagonals bisect each other.
Thank you for joining us. Be sure to try the tasks found in the Euclidean Geometry task video and to find more resources for this section on our website, www.mindset.co.za. After all that work, I need some brain food. I think I'm going to buy some joma fruit. Have you ever heard of it? It grows on the joma tree. Bye for now.